10 credits. You can type if you don't have a mic with you.
Well, not many people, perhaps.
I see. Yeah.
So maybe you halfway through the class you ask
Yes,
what the
yes. I just want to verify if they can actually see and then
Hmm.
submit a review. Then we are done. Yeah.
Hmm.
Okay, okay.
By the way, how can I see the projects?
I have sent you, you are a program chair for this thing. You have
Hmm.
to have an account in Open Review.
Mm-hmm.
And once you log in, I can show you maybe. Share. This will be useful for anybody who has joined also, not an issue. So, can you confirm if you can see my screen?
Yes, I can see your screen.
So once you log in, like this should say a Prasenjit saying here. It
So
should
I can
also
just
work.
go ahead and create an account, or how do I do it?
With the same email, I think I send it to.
So you sent
So,
me some link.
so it should be in your email. So here, if I go to program chairs, I have used. Let's see. So I have sent it to HRI. Do you want me to send it to your Gmail or?
No, no. Yeah, maybe you can send it to my Gmail also.
Okay, okay. I'll send you. So then once you receive, you just have to log in, and sign up.
Hmm.
Once you do the sign up, once you open your main page on the left hand side, you should see these two things. Program chair is
Hmm.
where you can handle and call for other reviewers and all the stuff. But Nizer 2025 MLMS, if you go, you hear because you are a program chair, you will see this. Other people won't be able to see.
Hmm.
And then if you go to active submissions, these are the three submissions we have. So if you can go and then click there, they have given their YouTube thing and then they have submitted their slides.
Hmm.
So, and
Okay.
then when people are here, they can just click on official review and then write
Hmm.
their criticism or whatever they want to write here.
Yeah. Okay.
Okay, stop sharing. Yeah.
Okay. So before I start today, I would also like to tell. Can you see me, or is there a problem with my video?
Yeah, I don't think I can see you either.
Yeah. Now you
Now,
can.
yes, yeah.
Mhm. So what I wanted to tell everyone is that we are roughly or just a little more than one third past one third of the course, and so far mostly we have been, at least I have done entirely formal stuff. Uh, we have been mostly covering formal stuff, but slowly we'll get into more hands-on, more practical things where you actually set things up and do calculations. So I want to do it in sort of three different modules, if you wish. One is the formal discussion that we are having right now. After this, I'll show you how to download data, how to organize your data, how to train models, and so on and so forth using scikit-learn and some of the databases that I showed you earlier. And the third part that I want to do is to discuss some of the key papers from literature. And that part will go beyond what we can do hands on, because those are somewhat advanced applications of machine learning, or we may not have access to all the data or some futuristic directions that application of machine learning AI is taking in material science, so that you are exposed to the directions this field is going. In fact, just today, this is to for your information, just today I shared someone's post on my LinkedIn account where this was a conference, some nature conference going on in China, and someone very well known in this area, actually from Dublin, Aaron Walsh. He just posted that sitting in that conference hall, just typing on his laptop, he just gives a command on his laptop, and an experiment, an autonomous experiment, gets started in some other city in China. So he is sitting in some city A. He just types something, gives a command on his laptop, and some lab gets operational completely automated way in some other city in China. So lab automation is, for those of you who do experiments, lab automation is going to be a very big thing going forward. So I'll just, for your information, so that you are aware of the directions this field is going, I'll discuss some of these things as we go along after we have done the hands-on things. Okay, so let us start with today's discussions. Let me share my screen. Yeah, I hope you can see my screen. So I'll just quickly recap what we were discussing last time. Oops. Yeah. So we were discussing two local features, ACSF, atom-centered symmetry functions. And there we discussed that within some cutoff distance, within some cutoff radius governed by this cutoff function, one constructs two body and three body functions that capture information about distances between atoms, angles between three atoms, and of course including their chemical identities through these superscripts z's or z1 z2 here for the three body functions. So that captures information about the local geometry about a central atom. So that was the whole idea, and I showed you that these are the this g2 g3 g4 functions, how they behave, what kind of information they can capture. Then finally, we came here, and there are some things that I want to clarify once again. Some of the things, I think there was a mistake in my counting last time. So let me correct this. So, first of all, I just go back to this figure on the top right here. So, we discussed various two body functions, two body quantities g1, g2, g3, etc. And these are the parameters, these eta and RAs are the parameters that determine the behavior of the G2 functions. G1 just depends on the cutoff function. So once you have defined your cutoff radius, that is fixed. So this is the cutoff function we talked about. RC is the cutoff radius. And depending on your system, depending on your chemical intuition, you fix some cutoff radius. After that, you have this eta and RS parameters governing G2 and this kappa parameter governing G3. So you can have one set of eta RS, or you can have multiple set of eta RS for the same material in the same calculation. Same for kappa. You can use one kappa or you can use different values of kappa and construct the features. And same for eta, zeta, and lambda for the G4 and G5 three body functions. And how are they arranged? They are arranged in the following way. It's not that you necessarily need to remember these things, because once this is internally coded in something called dscribe library, which I said we will discuss. after we finish these discussions. But then you should know that what is the count, so that of course you can get this information that given a material or given a certain types of elements that exist in your material set, what will be the size of this feature vector. Still, you should be able to do accounting yourself, so that you understand what is going on. So first of all, how are they arranged, how are they organized? So one body terms sorry two body terms for different values of z. So you have one central atom, and then z is varying for its neighbors. So for each neighboring z, g1, all the g2s, all the g3s are arranged sequentially like this. So g1s, then g1 for z1, then g2 for different sets of eta rs put together, then g3s for different sets of k1 kappa put together, and so on. Once you are done with the first uh, element as neighbor, you go to the second element. The first element could be hydrogen, the next one could be oxygen. So you write all these quantities in the same sequence for oxygen, and so on, depending on what all elements you have. Then the three body terms, you have the central atom, then you have to identify two other neighbors. They are identified by their atomic numbers. So in this example, 1 1, uh, 1 2, etc. So if you do not specify what are the elements present in your data set, by default describe will try to do it all the way from hydrogen, starting with z equal to 1 to z equal to some maximum value. I don't remember exactly how far it goes, and it will be a very large feature set which you really do not need, because probably you will have only a small subset of those elements in your training set. So you can sort of curtail that list. You can specify the elements that are present in your entire training data by defining a list called species. I showed you an example yesterday. We'll go through that example or those kinds of examples once again. But whatever those values are, so at this point, let us assume that we have these three or four elements in our training set: 1 2 3, z equal to 1 2 3 and 25. So if these are the elements present, then for the three body functions, and I'm calculating this ACSF around the z equal to 25 element, which is manganese. So then I can have both neighbors as this hydrogen, or hydrogen with helium, z1 2, then 1 3, and so on. Okay, and then you can try to do a count as to how many of these quantities you will have. But for that, you have to specify the sets of these parameters. So eta and rs for G2. Here I take only one set. For G3, I use two different kappa values, 1 and 2. And for G4 and G5, I have defined only one set of eta, zeta, and lambda, which is 1, 1, 1. This is just an example. So how many G1s you have? You will have 4 G1s. It will count 25 also, although 25 you have assigned or chosen as the center, because you have it in your species list. It will take Z as 25 also while constructing the G1s. So you will have 4 G1s similarly. So you will have G2, you have one set of eta RS. So you have 4 G2s for Z equal to 1, 2, 3, and 25. Suppose you have each of these elements only once in your, so one atom of hydrogen, one of helium, one of lithium, one of manganese. It's a strange thing, but suppose you have that, then of course there will be 25 will not have 25 as its neighbor. So that entry will be put as 0, and so on. What about G3? I have two different values of kappa, and I have four Z values here. So there'll be 8 different G3s. Okay. So 4 Z values and 2 kappa values. So those are the two body terms. And G4 and G5. So how many of these? I have only one set of parameters. So I have to count how many such pairwise combinations I can have. So and 1 2 and 2 1, so these are assumed to be, they are not calculated twice. So 1 2 is same as 2 1. In fact, 2 1 is not even written. Only one of these is written, either 1 2 or 2 1. So then what you have to find is how many of such combinations, pairwise combinations, you can have, so that you don't repeat the permutation of two numbers. And you can count for these four Z values. There are 9 such combinations, if I'm right. 1 2 3 4 5 6 7 8 9. So 9 different combinations of Z1 Z2. And because I have only one set of parameters, I'll have 9 entries for G4 and 9 entries for G5. If I had two sets of parameters, then we'll have 18 for G4, 18 for G5. So this will tell you what is the total number of these entries you will have. So that will give you the total length of your ACSF feature vector. So when you do a calculation with describe, you don't have to do any of these by hand. You have to learn how to use describe. That's an easy way of evaluating this, constructing these features. But you should perhaps check that what you think you are doing is correct and the number of features match with this estimation. Okay, so that is ACSF, atom-centered symmetry functions. The next thing we did was, or started discussing, was smooth overlap of atomic orbitals. So we could not finish the whole of it. So let me remind what we were doing. You have atoms in the unit cell constituting the elements. The first thing you do is you construct what I call uh, atomic density field for each type of element you have in your training set. So in this case, this is how, and these are the contributions. I have to do a correction here. Yeah. So if you focus on that formula, if an atom with atomic number Z is located at Ri, capital Ri, its contribution to the field value at some other point small r is goes down like a Gaussian. So, and you have to choose some appropriate sigma. So that's how the constructions, and if you have different, more than one Z elements, more than one elements of atomic number Z, then you sum their contributions at each of these points small r, and that's how you create the atomic density field for Z, the element with atomic number Z. And this way you create for all elements present in your training set. Now what do you do? You expand this function, this scalar function, rho of z, at the point r in terms of radial and angular distribution, basis functions, and CNLMs are the expansion coefficients. I discussed last time YLMs are natural basis functions for angular part of any function, and GNL here, they constitute the radial basis function. If GNLs are orthonormal, then you can find out these expansion coefficients by this integral. And we have assumed that g's are real functions, and we will use real functions. The g's are not complex, but YLMs are of course complex. I missed some indices here, so let me just put those in. Yeah, so those are my C's. And what I told you is that we are interested in, or we need to calculate C's, because with C's we can construct a rotationally invariant feature. So let's see how. Yeah. So before that, we have to resolve, or we have to decide what kind of radial basis functions we use. And so I said one type of radial basis functions that we use are called spherical primitive Gaussian orbitals. So the phi, the capital phi's that you see here, are the spherical primitive Gaussian functions, and their linear combinations are used as the radial basis functions g's. And you sum them over for a fixed L, you sum them over from this index n going from 1 to some maximum number n. And of course, alpha n is a decay parameter, which decides how fast these Gaussian functions decay. Now, GNs are in general not orthonormal, because Gaussian functions are not orthonormal, but it turns out that you can choose combinations of these Gaussian functions so that G's become orthonormal. So you can make them orthonormal. So in order to do that, what you do is first you calculate the overlap integral of these Gaussian functions. Okay, so this S in primed is the overlap integral between the functions phi n and phi n primed. I have suppressed the index L in some places to keep things simple. But as far as the Gaussian, whenever I'm talking of the Gaussian functions, there is also this L index. So this is the overlapping. So basically, it's the integral over the entire range of R of a product of two functions, phi n and phi n primed. So that is my Sn in prime. So it is like a matrix, right? Sn in prime is a matrix, which is a real symmetric matrix. So I define a matrix beta. Beta in primed also can be seen as a matrix. I define this matrix beta as s to the power 1/2. Now, what does that do? Now, see, if I choose beta to be s to the power 1/2, then when I calculate the scalar product of two functions, this gn and gm and gl, what do I get? So I just plug this in. So there is r square, and for gml, I have this part. Okay, you have to sit down and sort of look at these things when I share the slides. For the second function gnl, I have this part. Both are expanded in terms of the phi functions. And because betas are constants, I can pull them out of the integral. So I'm left with integral over products of phi's with some summation. So the summation I have not written because it's assumed that here I have assumed that repeated indices are summed over. So this I have beta m primed, beta n primed, and then this part, the integral is just Sm primed in primed from its definition. And because these matrices are real symmetric, I can just interchange this. So I have beta m primed here, Sm primed n primed here, beta n primed in here, and I know, or I have chosen my betas to be s to the 1/2. So when I write that, I just get a delta mn. So what that tells me is that this scalar product of two g functions is equal to delta mn, or in other words, they are orthonormal. So this is exactly what we wanted. So now we know how to construct g functions which are orthonormal. specific linear combinations of the Gaussians give us orthonormal G's. Then you are done. So then if G's are orthonormal, then you can use this expression that I showed you earlier to calculate C's. And you can do the same exercise for these polynomial radial functions. Same thing, same idea. So I'm not separately discussing this. I showed you shapes of these functions. Now what we are to understand is that this again will be a bit mathematical, but just this slide, and then we will get to our feature. So now suppose I'm doing a coordinate rotation. Okay, so this r here, r hat, is just sort of mathematical way of writing the rotation operator. So when I am applying this operation on my system, so the density will change in some way as an effect of this rotation. So this is just a formal operator acting on this whole thing. But then when I'm just doing a rotation, the r part really does not change. What changes is the ylm part, the theta phi part. That's all what is involved in rotation. So I can pull this rotation operator with the ylm part and leave this outside. Now it turns out that this rotation of this, or transformation of these YLMs under rotation, is a very widely studied topic in different branches, definitely in physics. So they can be written like this. So when you rotate YLM, basically it goes to, you go to a different set of axes, and after rotation, the effect of rotation can be written in as a matrix product like this. So some matrix acting on this YLM with summed over M primed. And this, so these are the matrices which represent the effect of rotation for a given L. So for a fixed L, DLs are 2L plus 1 by 2L plus 1 matrices, which give you the effects of rotation and which are called Wigner matrices. So this is what I had written here, except that now I'm writing the sums explicitly. So what I have done here is that this R operator acting on YLM is written in terms of the matrix, and sum over M primed is also explicitly written here. All the others are explicitly written here. Sum over M, sum over L, sum over M, and sum over M primed. Now that I have written all these things explicitly, I can write the D's with my C's. So I pull the D's, D and the C together, and this is what I have. And I have M index here, so I club the M summation with those, and then I have the M summation, the L summation, and the M primed summation outside. I'm just changing the order in which I write the summations. Nothing else has changed. But then this is, I can interpret this in a certain way. So I can consider, so given N and L, given the N quantum number, if I may call it so, and given the L index, I can view this as a matrix multiplication. Okay, provided I can view my C's for given N and L as a column vector. So if I do that, then what this does is basically, so I'm writing sum over M, C, N, L, M, D, L, M, M primed as C, N, L, M primed. So it's like transforming the column vector C under rotation. So just as I can view the rotation as having an effect on my YLMs, equivalently, I can view this as having some effect or equivalent effect on my expansion coefficients C's. So if I change my expansion coefficients Precisely in this manner, I have captured the effect of rotation on my uh, this density field. Good. So what do we do with that? This is how I wrote effect of rotation on my C matrix, or the C vector, or the coefficients C's. And this, in a formal way, in terms of the matrix D, can be seen as this. Okay? So CNL is the column vector for a given N and L. D is acting on it and giving me the transform column vector C primed NL. Now, D matrices has some special property. These are unitary matrices. So DL dagger DL. So for a given L, if I multiply, take the matrix multiplication of D dagger and D, I get the unit matrix. I now use that property here. So on the left hand side, I have C primed dagger and C primed. I write these in terms of C's and D's, and I use the unitarity of D. So D dagger D will give me just the unit matrix. So I get back C dagger. So basically, C prime dagger C primed turns out to be C equal to C dagger C for a given pair of NL. In other words, C dagger C is a quantity that remains invariant under rotations. So that is what eventually this relation tells me. Even if I apply a rotation, uh, the scalar product of the vector C with itself does not change. So this is the property we use to construct a rotationally invariant vector, feature vector. So for each, now remember we had this index Z, which we dropped because of, for the sake of convenience. We bring that in and we write this quantity Pn n primed L Z1 Z2 as this. Okay. For so these are products. This is not a, of course, it's a product, but this star is supposed to mean scalar, I mean, the complex conjugate of this CZ1 NLM. So CZ1 NLM, complex conjugated that, multiplying Cn primed LMZ2, and you sum over M, and the quantity you get on the left is P. This is, as we have shown, is rotational. Each of these C's is rotationally invariant. Therefore, this whole quantity is rotationally invariant. And these are, so you can calculate these for separate sets of values of N primed L, Z1, Z2, and concatenate all of these. And that's how you get what is called the SOAP, or the symmetric overlap of atomic positions. So that's the feature we were discussing. Okay, so it's finally the set of rotationally invariant quantities P's that give you the SOAP operator. Now I discussed all of these because these are the representations with which the entire thing, started. I mean, if you look at bit older papers like 4, 5, 6 years old, these are some of the features, or some of the feature based on chemical composition of the material. These were used to predict material properties. Slowly, we have moved on to more sophisticated representations, one of which is graph representation, which I will not get into for this in this course. But there is one representation which is also a global representation, which I discuss, and with that discussion, I will finish my discussion of materials representations. Um, I have discussed this. So this is what is called point cloud representation, or image based representation of materials. So both 3D image or voxelized image of materials have been used, and 2D images have been used. So you just you represent your material in a way which can be very well viewed as a 2D image. I will not discuss the 3D voxel image representations, but I will discuss three different types of 2D pixel image representations of materials. The first one, to my knowledge, this was the first one that was used. What else? So you, and all the examples I will show is for ternary materials. One can go beyond ternary materials, but I'm not aware of any published work going beyond ternary materials. And you already have a lot of uh, interesting chemistry within the, up to the ternary phase space. So what is the representation? It is best viewed as a sequence of blocks with certain number of rows and three columns. Three columns because we are talking about ternary materials, and it also is convenient because lattice structure can be conveniently uh, expressed by two sets of three numbers. So what are these? The first block here in this representation is the lattice matrix. Probably this is a bit too small, but let me see if I can make it a bit bigger. Yeah. So the first block here, A, B, C, alpha, beta, gamma, this is just the lattice vectors, lattice constants, and the lattice angles. That defines these six numbers, define your lattice structure. The next block here is, so ABC is the combination, a composition, or ANBLCM or something like that. So you have to give information about atom A. Where are those atoms? So if you have a certain number of A atoms, X1, Y1, Z1, X2, Y2, Z2. So these are the fractional coordinates of the A atoms sitting in the system within the unit cell. Next block is the same thing, the fractional coordinates in the unit cell of the B atoms. And the third one is fractional coordinates for the C atoms. So that defines the lattice structure, ABC, alpha, beta, gamma, fractional coordinates of all the atoms. But this has not yet defined what is the composition. So how many A atoms, how many B atoms, how many C atoms. And they pass that information to the model through something they called composition condition. So basically specifying if N, L, M are the numbers of A, B, C atoms, this information about individual numbers N, L, M is somehow passed on to the model. So that completely determines the structure. And so the last block, so you have given the structure, the lattice structure, the positions of the atoms in the unit cell, but you need something more, which is, ideally, which is like chemical properties of the elements that we have discussed before. This last block here, no, in this particular representation they did not give chemical information, but in the subsequent ones this was used. uh, and of course, because every to train a model, the lattice, the feature vector has to be of a definite length, definite size for each of the materials in your training sample. If the total number of, you have defined a total number of maximum atoms in your unit cell, which is n max. If a particular material has number of atoms which is less than n max, then you know pad the remaining rows with zero. So that is just the zero padding block. So that you have uh, n max plus 2 because of these two rows. Here n max plus 2 rows and 3 columns. So n max plus 2 times 3 pixel image as your materials representation. So this sort of simple idea was taken forward. Actually, this work, this is something that we developed, and The next one I'll show came first, then ours. But for the ease of explanation, I'm showing this first. Know that because you know your training set. So those many rows, and these are one hot encoded vectors. So if this row corresponds to z equal to 1, which is hydrogen, and if your first element A is hydrogen, then you put a 1 here. This one would mean that the second row is corresponding to helium. So the element C here is helium, and so on and so forth. And if you are talking of ternary materials, only three of these rows will have ones, the others will all be zeros. Then the next block is just the lattice matrix as before, A, B, C, alpha, beta, gamma. Then this block is the site coordinate matrix. So this gives the fractional coordinates of the atoms in the unit cell. And again, you have to define some maximum number of atoms that you can have, and you will have those many rows. Then you have to say, what is this atom? So this atom sitting at fractional coordinates 0.25, 0.75, 0.75. You have to give its identity also. That identity is given in this block. So this has exactly n max number of rows. This has exactly n max number of rows. And these blocks are tied to each other. So there is a correspondence between the first row here and first row here. So this would mean that an atom of identity A, which in our case is hydrogen, is sitting at 0.25, 0.75, 0.75. Correspondingly, for the second row, for the third row, and so on. And if you
Excuse
have
me, sir.
less than, yes, is there a question?
Sir, you have not shared the screen, sir.
Oh, and how long is that?
Uh, it's just for 2-3 minutes.
Okay,
In
no, I
between,
think
it got
something went
disconnected.
wrong. Yeah, something went wrong.
Okay, thank you, sir.
Um, yeah, so just stop me whenever you can't see my screen, okay? So, was explanation of this slide clear, or did you miss that?
Probably got missed.
Okay, so let me quickly go through this. So this is a image-based representation of a material, the first one that was reported in the literature. So I'm talking of a ternary material. Three different elements are present in the material: A, B, and C. And the material could be A, M, B, or AN. Let me write it out. So the material could be A, N, B, M, C, R. Okay. So N atoms of A, M atoms of B, and L atoms of C. So the first block has two rows, A, B, C, alpha, beta, gamma, gives you the lattice structure. Then the next block lists the fractional coordinates of all the A atoms in the cell. The next block lists all the fractional coordinates of the B atoms in the cell. And third block or the fourth block gives you fractional coordinates of the C atoms in the cell. The model is somehow given information about NML through something called composition condition. Let's not get into that detail. So overall, you have Nmax, that's the maximum number of atoms in the unit cell you have specified, plus 2 from this block, these many rows and 3 columns. So you can consider it to be an image which represents the material. This is an adaptation of that. So the first block is called element matrix, and the number of rows here is the maximum value of Z, the atomic number present in your training data set. The first row corresponds to hydrogen, second one to helium, This is Z equal to 2 for helium, and so on. Goes up to Z max. And if a hydrogen is present and your first element A happens to be hydrogen, you put a 1 here. So these are one hot encoded vectors which represent what are the ABC elements present in your material. Alpha ABC alpha beta gamma is the lattice matrix. Again, gives you the lattice structure. This block has n max rows and gives you the fractional coordinates of the atoms sitting in the unit cell. You have to give the identities of those chemical identities of those atoms as well. So this row is coupled to this row. There is a correspondence between row 1 in this block and row 1 in this block, which is the site occupancy matrix. So if I have have a one hot encoded vector like this tells me that the element A is present at this site 0.25, 0.75, 0.75. And from this block, I know that element A in my material is hydrogen. So I know that a hydrogen is sitting at this site. And this is how it goes for all the other rows. So this block has in max rows, this block has in max rows. And the last bit is you can have as many rows as you wish. But each row lists the chemical property of the some chemical property of the constituent atom. So the first row could be atomic number Z. The second could be electronegativity. The next could be group number, period number, and so on. It's up to you what are the properties that you want to include. So that gives you, again, this 2D pictorial representation of your material. What this represents, so this, as I told you, this is something that we introduced in the literature. You will find this in this paper if you are interested. We called it, what was the IRCR? I have to recall the full form of IRCR, but we called it IRCR representation. Um, the other the next the related thing is called FTCP, and this FT basically comes from Fourier transform. So this block, this part, so you see two distinct parts. You can see real space features and reciprocal space features. The real space features are exactly what the way we wrote IRCR representation. They had something extra here, which is reciprocal space feature. This entire part in the reciprocal space features is zero. These are all zero padded all the way here. The first non-zero thing appears here in this row, which is the last row of the site occupancy matrix. And then the real useful quantities are contained here, corresponding to the block containing chemical properties of the elements. Now, what are those? What are the entries in the reciprocal space? These are Fourier transforms of the chemical property captured or represented in this line. So if this line represents atomic numbers, these would be Fourier transforms of those quantities at different reciprocal space lattice vector. So different values of G, the reciprocal space lattice vectors represented by this HKL integers. So, and they in this particular work, they had this Fourier transform of various chemical properties at 59 different G vectors. And the line just above this, as I said, the last line of the site occupancy matrix contains the lengths of these G vectors. So lengths of G vectors and the Fourier transforms of those elemental chemical quantities at those G vectors. So they had 59 columns here. Only 3 are shown, but they had 59 columns, each for a different G. Now, this was reported, but then we did not see much merit in having Fourier transforms of elemental properties in the feature space, making it large with so much of zero padding. So we just simplified the thing and just used the real space representation, and it works just fine. Okay, so these are image-based representations of materials. And the interesting thing about this is these representations have been used both for property prediction and also for generative modeling. So generative modeling is something I think Dr. Mishra has also mentioned. I'm just talking, but we will not get into the technicalities of, we will not have this as part of this course. But these are generative models that can generate new materials once you have trained with your existing data set. So I think that sort of finishes my formal discussion of features representing materials. If you have any questions, feel free to ask, or you can send me questions over email if you wish. So the next class that I teach, I'll go over to how to access data from databases and how to construct features from those. So these features that we have discussed. So that's all. Let me check if there are questions. If not, I will hand it over to yeah. So as of now, there are, I don't see a question. No. Shubhankar, you want to take over now? You
Yeah,
wanted-
yeah. Okay. Good afternoon, all. This is specifically for the people who have registered for as a credit level course. I just wanted to understand that if you are able to log into Open Review and you can see other submissions as well. If few people can just confirm, then that will be nice. So just to make sure things are in plan, share window, yeah. Sorry, I've just shared the screen. It just basically shows Open Review. If you log in, it will look a little bit different to you. But on the left-hand side, almost I think those who have submitted, you should be able to see NISA 2025 MLMS. And under this active submissions, as a reviewer, you should be able to see that. I have added all of you as reviewers, those who have registered as credit for this course. If one of you can just confirm if you can see all the submissions, and if you click on a submission, are you able to see this button, official review? If yes, also I hope this exercise you can complete, and Friday I'll be taking the class. So you in case there are any issues, I'll try to solve it. Because I think it's due on 30th of October, on 30th of September, this one. But I think next week everybody will be in festive mode. So I hope you submit the review this week itself, and then get it done out of your way. Uh, thing. Fine. So I just want you to go to Open Review, check if you can see all the submissions. If yes, submissions, are you able to see this official review button or not? If yes, then you are free to submit your review. Like give it a, like, let's say, review from, let's say, team, and then you can write like team name, both of your names, and then just write the review and then just submit. Yeah, these points like rating and all these things, it's your choice. You can give them. It is mandatory to give. You can be neutral, and there is nothing personal. This is a discussion across the all the group. We just want everybody to understand what everybody else is doing, and so that you are not limited to what you are doing just. So it just increases the knowledge space. That's all. Yeah.
Yeah. So as for our records, we had some 12 or 13 people registering for credit. We have received 3 proposals, right?
Yes.
So which is 6 of them.
Yes. So I have Rahul, Navendu, Joyata, Hemant, Shubhankar, and Sulagna. I have
Yes.
6.
So those of you, if any one of you are present who are registered for credit but have not submitted your proposal without a project, you will not be evaluated and you will not get the credit.
Yes. But technically, they will not pass. Doesn't matter how good they score in exam. Yeah.
No.
Okay. Please let me know by Friday's class. Before Friday, I hope you have checked all this so that if anything has to be fixed, I can fix. Okay. Thanks a lot. Yeah. I'm done. Yeah.
Yeah. Okay.
Yeah.
Okay, then see you all on Friday.